Hey, this is Johannes, and this is going to be my presentation for security and computing. In this video, I'm mostly going to show how my model works, so it's going to be demo heavy, and along the way, I'll explain some of the context, some of the intuition behind how I built this project. So, to start off, I decided to build a machine learning model to detect unusual network traffic. And how I did that is to classify the incoming network as either VPN or a Tor data. And I'll explain some of the other um, classifiers later on. But I used something called the LSTM model, which is a popular, or it's a model that's used to train and predict on sequential data. So it's a type of recurrent neural network. And it's relevant here because normally networks are sequential by their nature. So, like, yeah, a simple synac, for example, um, happens in this particular order and this order only. Uh, and therefore, we need to build a model to have context and to understand what sequential data actually are. And so, how now you might ask what data set I used, and I used the darknet data set to train my model, which you can find in the Canadian Institute of Cybersecurity website. And I'll explain how they were able to generate the data set. I'll actually do that right now. So I'm gonna open Wireshark, and then I'm gonna open the Wi-Fi connection. Um, and then so if I just stop this capture. So normally a PCAP file just have lots of noise that the model doesn't understand. So what they did is convert this data set into what's called a flow, and I'll explain that. Just save this. Save it as a PCAP file. Save it to my downloads folder, and then I'm going to open my terminal. Copy. All right, so if I go to my flows test, we can see that we've converted that PCAP file into what's called a flow. And let me just open that. So what it's done is converts all those packet captures, and then it's transformed them into this file that contain a lot of features like total length forward, protocol type, flow duration, and there are a lot of features that the machine learning model can use to sort of understand what type of network that, that it's trying to predict. Um, and the darknet dataset that I used is actually labeled, and I'll open that right now. Save this. Uh, if you open my darknet CSV file, it's quite large, so it's going to take a second to load. So we can see that it's sort of similar to, or it has similar features to the packet capture that I had recently, or the pcap file. And then if we just go to the very right, we can see that this dataset is labeled as non-Tor. And then if we go further down, there's non-VPN data, and I'll explain what that means in a bit. And then it has Tor data, and finally it has VPN datasets. And each of these flows have their own features that the machine learning model can use to predict out of those different labels that I just mentioned. So I'm just going to close this. And then we go to, let's go to the code. And so what I did was I did the same thing that I just did for the normal traffic, and then I just generated a test VPN, a test Tor, and a normal PCAP flow. What that means is that for the test VPN, I just connected to a Proton VPN, and after some network traffic, I saved that, transformed that to a flow. And same for Tor data. I used a Tor browser and visited a couple of Tor websites to mimic what Tor network would look like. And all right, so let's just import some modules, and then if I have some of these files right here. So if I just read the data, we can see that we have the darknet dataset right here, and then we're just going to import some of the real data that I just saved. We can see that it's similar to the datasets that I downloaded. And then here we're going to do a bunch of cleaning, pre-processing. We're going to drop some columns that aren't necessary for the model to use. I'm going to do the same thing for my real data that I captured. And we're going to do that. If you notice, all of these features now have numerical data points, which is essential to the machine learning model for it to learn. And I did the same thing to my real-world data that I just captured. And at the end, the dataset is going to predict out of the couple of labels that I mentioned earlier, which is VPN, non-Tor, Tor, and so forth. So the darknet, for example, has a lot of data points, but I was only able to capture a couple of thousand. It actually takes quite some time to network to generate the PCAP file because I had to visit a bunch of websites and so forth. And then we can see that I have 78 columns, which means that my test normal does not contain the labeled data points, obviously, while the data frame or the darknet has the extra labeled column. And if we look at which features are actually used, or the best features that are used to correlate, or that are used to predict whether a network is a certain type of network, is so, I mean, obviously label is 100% correlated with itself, so we're not going to look at that. So if we look at backward packet length, flow bytes per second, and protocol, these are one of the main features that we use to predict whether the type of network. So backward packet length, the minimum backward packet length is the highest one. This one is actually used to predict the Tor network, especially because if we look at normal networks, they don't have any sort of encapsulation. But if we look at Tor and VPN data, they have an additional encapsulated headers that actually increase the size of the packets coming from the server. And I can have that So I have that in my file right here. So yeah, normal networks, so usually only the this part is encrypted using TLS. But if we use Tor or VPN data, especially in this case, actually encapsulates this part as well, and they hide your IP and destination addresses, which is essentially adding a new header, ESP header, um, to um, further encapsulate the packet, which adds additional uh, overhead into the network. It sort of slows down and then actually increases the size of the packet slightly. Same for onion routing, which for Tor data, which actually increases that further even more. And so that's why backward packet length minimum could be is actually a good indicator. And if we look at the same region flow bytes per second, adding additional headers means that the packets are larger and therefore larger amounts of data is being transmitted. And the protocol is that a VPN, if you're using a VPN, you're not necessarily using the normal protocol like TCP. You're actually using, depending on the VPN server that you use. So, for example, it could be WireGuard, it could be different protocols, and we can actually simulate that here. If I connect to a VPN really quickly here, and then if I open Wireshark and start a capture, we can see that if I just pause this, the protocols are actually mostly WireGuard because the VPN I'm using actually use WireGuard VPN server. And yeah, we can't actually search specific packets because IP addresses are encapsulated. Yeah. So if we look down, I'm just gonna save this. I'm gonna train my model. Then I'm gonna build a model. Now I'm not gonna train the model because I already trained it. So I'm actually going to load the model that I've already trained, which is my model. And then if we predict, since I split the data point into training and test data points, I'm just going to see how accurate that is. So if we look at here, its precision for predicting whether a network is VPN or not is 82%, and for Tor data, it's around 96%. And then for non-VPN data, which actually means network data that is either normal traffic or Tor, actually captures 89%, and then non-Tor means that it's networks that could be VPN or normal traffic, predicts 99% of the time. And that makes sense because since most of the networks that people use or are available are normal traffic, it has more of that data to see, which it then predicts that to be more accurate. So if we evaluate it, you'd see that the model is about 94% accurate, the model that I built. I mean, I could just show you this. This is what the LSTM model looks like, how to build the LSTM model. So if we just sort of understand what exactly this means. So yeah, so the data set that I used to train the model has only about 236 Tor data points and about 22,000 normal traffic, which makes sense because it's not that easy to capture Tor network data, especially because there's so few of it, so few network flows that involve Tor networks, whereas non-Tor data, which is a combination of VPN and regular traffic, usually dominates the network that most people use. So I'm just going to see how well my model does on real data that that I used. Um, let's see what that looks like. So for the VPN network that I captured, it has predicted 35 VPN networks and 36 non-Tor data and 64 non-VPN data points, which is good. It didn't detect any Tor data points. And then if we go down for test Tor data points, my model actually doesn't sort of see or label the Tor traffic at all. It has some VPN data, some non-VPN, and a couple of more non-Tor data points. And if we look at the normal, where I only captured normal networks, it actually does predict 7 Tor packets or 7 flows, and which doesn't make sense because I didn't use any Tor browser when I captured normal network traffic. I mean, this is likely because when I capture using Wireshark, a lot of background networks are going on that actually confuse the model when I pass in the flow, because the darknet dataset that that was used did a very good job of avoiding those noises, those background networks that were going on. And so I think some of the reasons why my model fell short was because even though I was capturing, so say for example, only VPN network, trying to simulate that, there was a lot of background networks going on that confused the model. And so yeah, this is what I tried to do.